We'll start in about a minute. Today we'll cover section 7.3 on the unit circle. So in the xy plane, the unit circle is centered at the origin, that is the ordered pair 0, 0, and its radius is 1. If the ordered pair xy is a point on the unit circle that corresponds to a central angle in standard position whose measure is t, then the x-coordinate is equal to cosine of t, and the y-coordinate is equal to sine of t. So I'll attempt to draw this. We have the xy plane and a central angle t, and this point is on the unit circle, so that means the radius is 1. So if I sketch in the unit circle, part of the unit circle, it will look something like this. But if you notice, we can construct a right triangle, and this value on the horizontal side of the right triangle I'll call x, and this vertical side I'll call y. And then if we take cosine of t, that's adjacent over hypotenuse, x over 1, or x, and sine of t is the opposite side over the hypotenuse, y over 1, or y. So the x-coordinate of this point is equal to cosine of t, and the y-coordinate of the point is equal to sine of t. Okay, so that is going to be the case for any point that's on the unit circle. We just need to know what the central angle is. As a reminder, in the xy plane, just in general, so we have the first quadrant on the upper right, and then counterclockwise the second quadrant, and then the third quadrant on the lower left, and the fourth quadrant on the lower right. So in the first quadrant, we know that the x values are greater than 0 and the y values are greater than 0. So what does that mean with regard to the trigonometric functions? Well, if t is an angle in the first quadrant, then cosine of t must be positive and sine of t must be positive because the x and y coordinates are positive. In the second quadrant, well, the x values in the second quadrant are negative, so those are less than 0. But the y coordinates, since they're above the x-axis, they're positive, so y is greater than 0. So in terms of sine and cosine, if you have a terminal angle in the second quadrant, if the terminal angle is t, then cosine of t is negative or less than 0 in the second quadrant, and sine of t is greater than 0 in the second quadrant. So we'll just do a couple more of these. In the third quadrant, well, the x-coordinates are negative and the y-coordinates are negative, so x is less than 0 and y is also less than 0. So if you have a terminal angle in the third quadrant, then the cosine of that angle is negative, and the sine of that angle is also negative. And then finally, in the fourth quadrant, the x-coordinates are positive, and the y-coordinates are negative. So for a central angle that terminates in the fourth quadrant, cosine of that angle will be positive, and the sine of that angle will be negative. Okay, our next little exercise, find the sines and cosines of the quadrantal angles. So the quadrantal angles in degrees, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Each of those has a terminal side on an axis. In radians, those are 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians. On the unit circle, well, on the x-axis, if the radius is 1, this ordered pair is 1, 0. On the y-axis, this ordered pair is 0, 1. On the negative x-axis, on the unit circle, I'm plotting points on the unit circle, and I'll draw the unit circle in a minute. But this point on the unit circle, the x-coordinate is -1 and the y-coordinate is 0. And then on the negative y-axis, this point on the unit circle, the x-coordinate is 0 and the y-coordinate is -1. So I'll try to draw a circle. So pretend like this is a circle of radius 1. And incidentally, the algebraic equation for that circle centered at 0, 0 with radius 1 is x squared plus y squared equals 1. You might have learned that in an algebra class at some point. Okay, so this terminal angle, this could be 0 degrees or 360 degrees, or 0 radians or 2 pi radians. So we can say that since the x-coordinate is cosine of the central angle, we can say that cosine of 0 equals 1, because the x-coordinate is 1, and sine of 0 is equal to 0. So I'm just going to use the radian measure for the central angles. Okay, on the positive y-axis, well, this time, let's see, the central angle for this is pi over 2 radians. The x-coordinate of this point is 0, the y-coordinate is 1. So that means that cosine of pi over 2, that's equal to the x-coordinate, which is 0. And sine of pi over 2, that's equal to the y-coordinate, which is 1. So sine of pi over 2 is 1. Okay, the next quadrantal angle is pi radians. So when the central angle is pi radians, the x-coordinate on the unit circle is -1 and the y-coordinate is 0. So this means that cosine of pi, equivalent to cosine of 180 degrees, is -1. And the sine of pi is 0. Well, we'll just do one more. When the central angle is 3 pi over 2, or 270 degrees, the x-coordinate of this point on the unit circle is 0, the y-coordinate is -1. So that means cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is -1. I'll just mention, if you have one complete revolution, then we're back at the ordered pair 1, 0. I guess I can write those down somewhere. Cosine of 2 pi, that's one revolution. The x-coordinate is 1. So cosine of 2 pi is 1. And sine of 2 pi is the y-coordinate, which is 0. Okay, so make sure that you know all of these values for sine and cosine at the quadrantal angles. Okay, we're going to use the unit circle and the sine and the cosine to derive what is called the Pythagorean identity. And we'll make use of this algebraic equation for the unit circle centered at the origin, x squared plus y squared equals 1. Okay, so if I just pick any point on the unit circle that I want, just as a representative, then we know that the x and y coordinates are equal to cosine of t for x and sine of t for y. Well, if we replace, in this equation, if we replace x with cosine of t and replace y with sine of t, we get the Pythagorean identity. So x squared is cosine of t squared, or cosine of t squared written this way, plus sine of t squared equals 1. So just to reiterate, since cosine of squared t, or cosine of t squared plus sine of t squared equals 1, since x equals cosine of t, y equals sine of t, and for the unit circle, x squared plus y squared equals 1. This is referred to as a Pythagorean identity. There are two other Pythagorean identities that we will also encounter at some time later. But this is perhaps the most famous of the Pythagorean identities. So make sure that you automatically know upon seeing cosine of t squared plus sine of t squared, that has to equal 1. Okay, next page. Use the Pythagorean identity to solve the problems. If sine of t equals 2/5 and t is in the second quadrant, find cosine of t. Let's first note that since t is in the second quadrant, the cosine of t must be negative, because in the second quadrant, all of the x coordinates are negative. Okay, so I'll rewrite the Pythagorean identity over here, cosine of t squared plus sine of t squared equals 1. So if sine of t is equal to 2/5, then we can replace sine of t with 2/5. So 2/5 squared, since this has sine of t squared, and this equals 1. So now all we have to do is solve for cosine of t, and we'll remember that since t is in the second quadrant, cosine of t has to be negative. Okay, so cosine of t squared is equal to 1 minus the fraction 2/5 squared. When you square that fraction, you get 4/5, so it's 1 minus 4/5. Sorry, 4/25 when you square 2/5. And then we'll write this as a single fraction. 1 is equivalent to 25 over 25. And 25 over 25 minus 4 over 25 is 21 over 25. So in general, we would say that when we apply the square root property, cosine of t is equal to positive or negative square root of 21/25, which we can write as positive and negative square root of 21 over 5. But since t is in the second quadrant, since t is in quadrant 2, the cosine of t value that we want is negative square root of 21 over 5. We'll do one more like this. If the cosine of t is equal to 16/25 and t is in the fourth quadrant, then find sine of t. Since t is in the fourth quadrant, the lower right quadrant, then the y coordinates are negative, so sine of t must be negative. Okay, so we'll use the Pythagorean identity again, cosine of t squared plus sine of t squared equals 1. And we'll replace cosine of t with 16/25. So we'll have 16/25 squared plus sine of t squared equals 1. And when you square the fraction 16/25, you get 256 over 625. So sine of t squared will be 1 minus 256 over 625. And we can replace 1 with 625 over 625. So it has a common denominator. And let's see, the denominator 625. And if we subtract 250, then we're at 375. So we get 369 over 625. That's what sine of t squared is. And in general, we would say that when we apply the square root method, sine of t is equal to positive or negative square root of 369 over 625, or positive or negative. We can tell that 9 is a factor of 369, and 9 is a perfect square. It looks like 9 times 41 is equal to 369. So this is positive and negative square root of 9 times the square root of 41. And then in the denominator, the square root of 625, which also simplifies. So sine of t, the two possible values are positive and negative 3 times the square root of 41 divided by 25. But since t is in quadrant 4, sine of t is negative there. So our solution, sine of t, is equal to the negative of 3 times the square root of 41 over 25. Okay, our next exercise, well, what we're about to do next is similar to what we've already done, what we did yesterday. But I'll try to use the unit circle to do it this time. If t is equal to pi over 4, we know that that's equivalent to a 45-degree angle. So in the first quadrant, I'll attempt to draw a 45-degree angle. Radius is 1, or pi over 4 radians. So this is a point on the unit circle. So I'll sketch in a portion of the unit circle. And if we construct a right triangle, and I'll refer to this side as length x, but since it's a 45-degree angle, it's an isosceles right triangle. So the vertical side is also, that's equal to the horizontal side. So I'm just going to say that that's x. So we use the Pythagorean theorem on this right triangle to solve for x. So we get 1 squared equals x squared plus x squared, which is 2x squared, or x squared equals 1/2. And so x equals, in the first quadrant, x equals positive 1 over the square root of 2. Okay, so the x coordinate of this point is 1 over the square root of 2, and the y coordinate is also 1 over the square root of 2. So since it's a point on the unit circle and the central angle is pi over 4, then cosine of pi over 4, that's equal to the x coordinate, 1 over the square root of 2. You can write it as the square root of 2 over 2 if you want. And the sine of pi over 4, that's equal to the y coordinate, is also 1 over the square root of 2. Okay, so these are sine and cosine values evaluated at pi over 4 that you should learn so that you know them automatically. Okay, if the central angle is pi over 6, I'm sure you all know what sine of pi over 6 and cosine of pi over 6 are already, but we'll go through this derivation. So in the first quadrant, we have this 30-degree angle, or pi over 6. And here's a point on the unit circle. The radius is 1. And we can construct a right triangle. So what we do in this derivation is we construct another triangle below the x-axis so that this angle is also pi over 6. This angle up here is pi over 6, sorry, pi over 3. And this angle is altogether is pi over 3. So 60 degrees. So what we have is an equilateral triangle. And so if we label the x-coordinate x, which is this length of this right triangle, and since this is also this is equal to 1 because the big triangle is equilateral, so that means that this side right here is 1/2, so the y-coordinate is 1/2. And we can use the Pythagorean theorem to determine what the value of x is on this side of the right triangle. Okay, so 1 squared equals x squared plus the fraction 1/2 squared. And so x squared is equal to 1 minus 1/4, which is 3/4. And so x will be, in this case, will be the positive square root of 3/4, or the square root of 3 over 2. Okay, so the x-coordinate is the square root of 3 over 2. So we'll just write down what we already know. Cosine of pi over 6, that's equal to the x-coordinate of that point on the unit circle, but we found it to be equal to the square root of 3 over 2. And the sine of pi over 6 is the y-coordinate of this point on the unit circle, which is equal to 1/2. Well, I'll save you the misery of going through another derivation, but we'll at least write down cosine of pi over 3 and sine of pi over 3. I'll remind you of something we talked about yesterday. Cosine of pi over 3 is equal to sine of pi over 6. Which is equal to 1/2. So cosine of pi over 3 is 1/2. Sine of pi over 3, well, that's equal to cosine of pi over 6, which is the square root of 3 over 2. So hopefully you'll remember that from yesterday. Okay, let's move on then to the next page. Okay, scientific calculators nowadays have both degree and radian modes for evaluating trigonometric functions. If a calculator only has the degree mode, then the calculator can still be used to evaluate a trig function of a radian measure. So for example, if theta equals 2 pi divided by 9 radians, you can find the decimal approximation of sine of theta using a calculator that only has the degree mode. So we talked about this a little bit yesterday. We convert 2 pi over 9 radians to degrees if we multiply by 180 degrees over pi radians, and then simplify. So the pi divided by pi equals 1. 9 goes into 9 once and into 180, 20 degrees, and then 2 times 20 degrees is 40 degrees. So that means that sine of 2 pi over 9 radians is equal to sine of 40 degrees. So if you have a really old calculator, then it might only have one mode, but you can always convert from radians to degrees if you have to. Okay, here's a comment about the domain and range of sine and cosine functions. So the central angle can be any real number, because if we just rotate any number of times that you want around the circle, the central angle can be any real number between negative infinity and positive infinity. So the domain of the sine and cosine functions are all real numbers from negative infinity to positive infinity. But the range is between -1 and 1, including the endpoints -1 and 1. Okay, finding reference angles. We've encountered reference angles already. Given an angle t, the reference angle t prime can be used to evaluate the trigonometric functions at t. So this is a very useful and an important concept. It's not too hard, but just make sure that you know how to do it. So suppose we have an angle t that's in the second quadrant. So its terminal side is in the second quadrant. So that's t. And we'll assume that this point is on the unit circle, so the radius is 1. And we're going to label the reference angle t prime. So remember that reference angles, we always pick a positive number that's between 0 and 90 degrees to represent the reference angle. Okay, so since t is in the second quadrant, well, we know that sine of t is positive. So the sine of t has the same value as the sine of the reference angle t prime. Okay, but we also know that in the second quadrant, the y-coordinates are positive, but the x-coordinates are negative. So cosine of t is equal to the negative of cosine of t prime. So cosine of t prime has to be positive because t prime is a number between 0 and 90. But since t is in the second quadrant, we know that it has to be the negative of cosine of t prime. Okay, well, what about tangent of t? Well, the tangent, since it's opposite over adjacent, the tangent of t will be negative when t is in the second quadrant. So this is going to be equal to the negative of tangent of t prime. Okay, so this is the useful part of knowing how to find reference angles, and then just keep in mind what the signs of, that is positive and negative, of the sine and cosine functions in each of the quadrants. Okay, well, what if we have a central angle in the third quadrant? So a central angle in the third quadrant. So here's our value of t. And the reference angle is just this angle, t prime. But remember, t prime is, we're just taking the positive measure of that angle. In the third quadrant, the x-coordinates are negative and the y-coordinates are negative. So since t is in the third quadrant, we know that cosine of t is negative and sine of t is also negative. But cosine of the reference angle is positive, and the sine of the reference angle is also positive. So in this quadrant, cosine of t is equal to the negative of cosine of the reference angle t prime, and sine of t is equal to the negative of sine of the reference angle t prime. Okay, finally, in the fourth quadrant, we have a central angle whose terminal side is in the fourth quadrant. So that's t. In the fourth quadrant, x-coordinates are positive, so that means cosine of an angle t that's in the fourth quadrant is positive. But the y-coordinates are negative, so sine of t will be negative. The reference angle is t prime. So cosine of t will be exactly the same as cosine of t prime. And sine of t will be equal to the negative of sine of t prime. Okay, this might make more sense if we look at some numerical examples. Yeah, this one, given an angle t, find the reference angle t prime and use it to evaluate sine of t, cosine of t, and tangent of t. So if t is equal to negative 300 degrees, that's a clockwise revolution. So let's see, from the positive x-axis, negative 270 is on the positive y-axis. So negative 300 is right there, we'll see. So that is negative 300 degrees. Make sure you're careful when you're finding reference angles. The reference angle is the angle formed by the terminal side and the horizontal axis. So this angle is the reference angle, and we can tell that it's going to be 60 degrees. Well, since the terminal side of negative 300 is in the first quadrant, sine and cosine are positive, and so is tangent. So we can say that tangent, let me start with cosine of negative 300 degrees is equal to cosine of 60 degrees. And we know that cosine of 60 is equal to 1/2. And sine of negative 300 is equal to the sine of 60 degrees, and that's equal to the square root of 3/2. And tangent is also positive in the first quadrant, so tangent of negative 300 degrees is equal to the tangent of 60 degrees. So we're eventually going to get into the fact that the tangent of 60 is equal to the sine of 60 divided by cosine of 60. So we might as well do that now. Sine of 60 is the square root of 3/2. Cosine of 60 degrees is 1/2. And then this will simplify to the square root of 3. Okay, the next example, t is equal to 13 pi over 6. So what's the reference angle on that one? Notice that 13 pi over 6 is equal to 12 pi over 6 plus pi over 6, or 2 pi plus pi over 6. So this angle, if you wanted to draw it, it's one full rotation plus pi over 6. So I'll just write the pi over 6. Yeah, maybe I better do it. Okay, so one complete revolution and then plus a little bit. So that's 13 pi over 6. And the reference angle is pi over 6. Okay, so cosine of 13 pi over 6. Since we ended up in the first quadrant, cosine of 13 pi over 6 is equal to cosine of the reference angle pi over 6. And this is the square root of 3/2. And sine of 13 pi over 6 is equal to sine of pi over 6, which is equal to 1/2. And the tangent of 13 pi over 6 is equal to the tangent of pi over 6. But this is equal to sine of pi over 6 divided by cosine of pi over 6. So sine of pi over 6 is 1/2 divided by cosine of pi over 6, which is the square root of 3 over 2. This simplifies to 1 over the square root of 3. Okay, a couple more. Well, you get better with practice, even though it's monotonous. So we have this angle, t equals 5 pi over 4. So where is that angle? Well, 5 pi over 4, notice the fraction 5/4. 5/4 is bigger than 1. So you can think of 5 pi over 4 as pi plus pi over 4. And so this angle is in the third quadrant. So if we just went from the positive x-axis to the negative x-axis, that would be pi. And then we go pi over 4 more, which is equivalent to 45 degrees more. So here is 5 pi over 4. And the reference angle is pi over 4. Okay, but our angle 5 pi over 4 is in the third quadrant. In the third quadrant, x values are negative and y values are negative. So that means cosine of 5 pi over 4 is equal to the negative of cosine of the reference angle pi over 4. And we know that cosine of pi over 4 is 1 over the square root of 2. So cosine of 5 pi over 4 is equal to the negative of 1 over the square root of 2. Sine of 5 pi over 4. Well, sine is in the third quadrant. Sine is also negative. So sine of 5 pi over 4 is equal to the negative of sine of pi over 4. And sine of pi over 4 is also 1 over the square root of 2. So this will be equal to negative 1 over the square root of 2. And finally, the tangent of 5 pi over 4, that's equal to the tangent of pi over 4. Tangent is positive. Tangent is positive in the third quadrant. If you remember, tangent of an angle is equal to the sine of the angle divided by the cosine of the angle. So if we divide sine by cosine, a negative divided by a negative is equal to positive 1 in this case. Okay, one more. So this is a long section, but it's important, so let's keep going. T equals 23 pi over 6. Well, 12 pi over 6 is 2 pi, so you can think of 23 pi over 6 as 2 pi plus 11 pi over 6. So this angle is 1 complete revolution plus 11 pi over 6. So it's not quite 2 complete revolutions. It falls short of 2 complete revolutions by pi over 6. Okay, so we might as well sketch in the rotation. So counterclockwise, there's 2 pi, and then an additional 11 pi puts us somewhere in that region right here. Okay, so this is 23 pi over 6. So what's the reference angle? This reference angle is pi over 6, or 30 degrees. Okay, so since we ended up in the 4th quadrant, we know that the x values are positive, the y values are negative. So cosine will be positive, sine will be negative. Okay, so cosine of 23 pi over 6 will be equal to the cosine of pi over 6, which is positive square root of 3 over 2. But the sine will be negative. The sine of 23 pi over 6 will be equal to the negative of the sine of the reference angle pi over 6, which is negative 1/2. And the tangent will be negative. Tangent of 23 pi over 6. I'll just write what sine is. Negative 1/2 in the numerator. The denominator is the square root of 3 over 2. So this will become negative 1 over the square root of 3. So just to reiterate what I did in this last step, I'm using an identity. Tangent of theta is equal to sine of theta divided by cosine of theta. Okay, now we'll look at a different, not quite so different. We did something kind of like this earlier. If cosine of t is equal to 1/7, and t is in the 4th quadrant, find sine of t. Since t is in the 4th quadrant, sine of t has to be negative. So I'll just remind you of the Pythagorean identity that we can use to help us solve this problem. So cosine of t squared plus sine of t squared is 1. So we replace cosine of t with 1/7. So cosine of t squared will be 1/7 squared plus sine of t squared plus sine of t squared equals 1. And so sine of t squared will be equal to 1 minus 1/49th, because 1/7 squared is 1/49th. And then this will become 48/49. So when we apply the square root property, if sine of t squared is 48/49, sine of t is equal to the positive and negative square root of 48/49. And we can simplify this. The square root of 48 is 4 times the square root of 3 in the numerator, and the denominator, the square root of 49, is 7. But since the central angle T is in the fourth quadrant, we want the negative solution. So sine of T is negative 4 times the square root of 3 over 7. Okay, next page. More tediousness follows. So we saw these earlier. Well, a couple of them. Sine of pi over 2 is 1. You can use the unit circle to help you remind you of that. Cosine of pi over 2 is 0. So remember the quadrantal angle pi over 2, and on the unit circle, the ordered pair is 0 for x and 1 for y. Tangent of pi over 2. So let's use the fact that tangent of theta is equal to sine of theta over cosine theta. So tangent of pi over 2 is equal to 1 divided by 0. But remember, division by 0 is undefined. So tangent of pi over 2 is undefined. So that will be an important thing to remember in the coming days. Cotangent of t, in general, cotangent of t is the reciprocal of sine of t. Or you can think of cotangent of pi over 2, in this case, as cosine of pi over 2 over sine of pi over 2. So hopefully that makes sense. Since tangent and cotangent are reciprocals of each other, then the reciprocal of tangent is what cotangent is. Okay, well, cosine of pi over 2 is 0, and sine of pi over 2 is 1, and 0 divided by 1 is 0. So there's nothing illegal going on here. So although tangent of pi over 2 is undefined, cotangent of pi over 2 is equal to the number 0. Okay, we have some more examples of angles. We'll want to find the reference angles, identify the quadrant of the terminal angle, and then evaluate sine and cosine. Okay, so 225 degrees. So if we move counterclockwise, there's 180, so plus 45. So there is 225 degrees. The reference angle is 45 degrees. And since 225 has a terminal side in the third quadrant, both cosine and sine are negative. So cosine of 225 That's equal to negative cosine of the reference angle, 45 degrees. So that's negative 1 over the square root of 2. And sine of 225. In the third quadrant, sine is also negative. So sine of 225 is the negative of sine of 45 degrees, which is also negative 1 over the square root of 2. Okay, the next angle, negative 120. So what quadrant is that in? Okay, so this time we move clockwise from the positive x-axis. So from here to here, that's negative 90, and then a little bit more, we're at negative 120. So what's the size of the reference angle? The reference angle, well, to get all the way to the negative x-axis, we would have to go a total of negative 180. So the reference angle is 60 degrees. So remember, reference angles, we always we think of them as positive numbers between 0 degrees and 90 degrees, or 0 radians and pi over 2 radians. Since the terminal side is in the third quadrant, then sine and cosine are both negative. Okay, so cosine of 120 is equal to the negative of cosine of 60. Cosine of 60 is 1/2, so we get negative 1/2 for cosine of 120. And then sine of 120 in the third quadrant, sine is also negative. So this is the negative of sine of 60. So negative square root of 3 over 2. So counterclockwise 330 degrees. Well, there's 90, 180, 270. Well, all the way, one complete revolution is 360 degrees. Okay, so here is our 330 degree revolution. And the reference angle is 30 degrees. Okay, in the fourth quadrant, cosine is positive because the x values are positive, and sine will be negative because the y coordinates are negative. Okay, so cosine of 330 degrees is equal to cosine of 30 degrees because they're both positive. And this is the square root of 3 over 2. And the sine of 330 degrees is equal to the negative of the sine of 30 degrees, or negative 1/2. Okay, let's do some more. 5 pi over 3. So where is that? Where's the terminal side of 5 pi over 3? Well, it's almost 6 pi over 3, which is 6 pi over 3 is 2 pi. So it's not quite one revolution in the counterclockwise direction. So counterclockwise, pi over 2, pi, 3 pi over 2. And then about that much. So this is 5 pi over 3. The reference angle is pi over 3. So it's in the fourth quadrant. Cosine is positive and sine is negative. Okay, cosine of 5 pi over 3 equals cosine of pi over 3, positive 1/2. And sine of 5 pi over 3 is equal to the negative of sine of pi over 3. So this is negative square root of 3 over 2. Okay, the next angle, negative 7 pi over 4. So this time we move clockwise. This is not as far as negative 2 pi would be. Negative 8 pi over 4 is negative 2 pi. So it's a clockwise revolution that's falls short of one complete revolution. It falls short by pi over 4. So it's a clockwise revolution. So here's negative 7 pi over 4. And the reference angle is pi over 4. The terminal side is in the first quadrant. So both cosine and sine are positive. So we'll go ahead and write it down. Cosine of negative 7 pi over 4 equals cosine of pi over 4, which is equal to 1 over the square root of 2. And sine of negative 7 pi over 4 equals sine of pi over 4, also equal to 1 over the square root of 2. Okay, 5 pi over 6. So where is the terminal side of this angle? Notice the fraction 5/6. That's a little bit less than 1. So counterclockwise, we don't have quite 1/2 of a revolution. So here's 5 pi over 6. The reference angle is pi over 6. The terminal side is in the second quadrant, so cosine is negative and sine is positive. Okay, so cosine of 5 pi over 6 is equal to the negative of cosine of pi over 6, which is the negative of the square root of 3 over 2. And sine of 5 pi over 6 is equal to the sine of pi over 6. They're both positive. And sine of pi over 6 is 1/2. So I hope all of this practice using reference angles is going to pay off, especially evaluating sine and cosine at the special angles. Okay, the next problem, find the coordinates of the point on a circle with radius 20 corresponding to an angle of 120 degrees. So it should be stated in the problem that the circle is centered at 0, 0. Otherwise, if we didn't make that assumption, then we wouldn't know how to answer it. Okay, well, this is not too bad. First, let's find where 120 degrees is. So counterclockwise, so there's 90 and then 30 more, we're at 120 degrees. And here we're assuming that the radius of the circle is 20. The reference angle is 60 degrees, or yeah, 60. Okay, and since the radius of the circle is 20, what we're trying to do is we're trying to find the x and y coordinates of this point that's on the circle with radius 20 centered at 0, 0. And it's not going to be too hard. The x coordinate is just going to be 20 times cosine of 120. But cosine of 120 is negative, right? The cosine is negative in the second quadrant. So we can write this as 20 times the negative of cosine of 60 degrees, which is 20 times negative 1/2, or negative 10. And that seems to make sense because this point in the second quadrant has an x coordinate that's negative, and the y coordinate of that point will be positive. So it's 20 times the sine of 120 degrees, or 20 times the sine of the reference angle 60 degrees. And the sine of 60 is the square root of 3 over 2. And this will be 10 times the square root of 3 for the y coordinate. The next problem is similar. I'll leave this next one for you to do. You can just mimic what we did on the previous one. Okay, next thing we'll do is find the following products. So we want to multiply sine of 11 pi over 3 times cosine of negative 5 pi over 6. So if you thought what we were doing was bad, this is twice as bad, because we have to find what the sine of one angle is multiplied by the cosine of a different angle. So we're going to use reference angles to help us. So let's first focus on 11 pi over 3. So 11 pi over 3 well, let's see, down here I'll write 11 pi over 3. 6 pi over 3 is 2 pi, so you can think of 11 pi over 3 as 2 pi plus 5 pi over 3. So this angle has 1 complete revolution plus 5 pi over 3 after that. And 5 pi over 3 is in the fourth quadrant. So 11 pi over 3 is in the fourth quadrant. I won't do all of the winding. I'll just write down where it ends up. And I'll do this part. So this is where the 11 pi over 3 terminates. And so the reference angle is pi over 3. Hey, and we know that in the fourth quadrant, sine is negative. So we'll keep that in mind. Now let's focus on the other angle, negative 5 pi over 6. Okay, so this is clockwise. Well, negative 5 pi over 6 won't quite make it to the negative x-axis. It will fall short by pi over 6. So this is negative 5 pi over 6. And the reference angle is pi over 6. Since this is in the third quadrant, both cosine and sine are negative. For this angle, we're just noting that cosine will be negative in this quadrant. Okay, so let's just write down what we know. We won't write all of the details like we did in the previous problems. So we know that since 11 pi over 3 has a terminal side in the fourth quadrant, sine will be negative. So we'll just replace sine of 11 pi over 3 with the negative of sine of pi over 3. And then we're going to multiply that by cosine of negative 5 pi over 6. This is in the third quadrant and cosine is negative, so this will be the negative of cosine of pi over 6. And then we'll just write down what we know. A negative times a negative is a positive. Sine of pi over 3 is the square root of 3 over 2. And cosine of pi over 6 is also the square root of 3 over 2. So when we multiply those, we just get 3/4. Well, let's try. We won't do all of these, but these are good exercises for you to work on at some other time. Let's just do, I guess we'll do the next one. So, no, wait. Oh, that's all right. Sine of negative 9 pi over 4. Well, notice negative 8 pi over 4 is 1 complete revolution clockwise. And so it goes beyond 1 revolution by pi over 4. So it goes 1 complete clockwise and then an additional pi over 4. I guess I should write that in. So clockwise, one complete revolution, and then pi over 4 more than one complete revolution. So this is negative 9 pi over 4. And the reference angle is pi over 4. And in the fourth quadrant, sine is negative. We'll keep that in mind. Okay, then cosine of negative pi over 6. Okay, so we have a clockwise revolution of pi over 6 radians. So there's negative pi over 6. And the reference angle is pi over 6. So that's not so bad. And we know that in the fourth quadrant, cosine is positive because the x-coordinates are positive. Okay, so we can write down, without writing all of the details, in the fourth quadrant, sine is negative. So sine of negative 9 pi over 4 is the negative of sine of pi over 4, using the reference angle. And we'll multiply that by cosine of pi over 6, because cosine is positive in the fourth quadrant. And sine of pi over 4 is 1 over the square root of 2, so this is negative 1 over the square root of 2. And cosine of pi over 6 is the square root of 3 over 2. So we can write this as negative square root of 3 over 2 times the square root of 2. For a few minutes, we'll do some some review problems that we started on yesterday. So we started this problem yesterday. A bike with 24-inch diameter wheels is traveling at 15 miles per hour. Find the angular speed in radians per minute, and also find the wheel's revolutions per minute, or the RPMs. Okay, so the linear velocity is given. 15 miles per hour is the linear velocity. And we're supposed to find the angular speed in radians per minute. So remember that the linear speed is equal to the radius times the angular speed. And this means that the angular speed, omega, is equal to the linear speed divided by the radius. Well, we know what the radius of the bike wheel is in inches. Since the diameter is 24 inches, the radius is 12 inches. So what that means is we want to find what the linear speed is in inches per minute instead of miles per hour. Okay, so we can do that. Let's focus on converting 15 miles to inches first. In 1 mile, we know that there are 5,280 feet. So 5,280 feet divided by 1 mile. This is like multiplying by 1, just in different units. And when I multiply 15 miles per hour by 5,280 feet over 1 mile, the miles units cancel. And then we're going to convert feet to inches. So every foot has 12 inches. 12 inches divided by 1 foot. So the feet units cancel. So now I have the velocity measured in inches per hour. So I ran out of space over here, so I'm going to rewrite this and just write it as, I'm going to leave it in factored form for now, 15 times 12 times 5,280 inches per hour. And then we're going to convert the units from inches per hour to inches per minute. This won't be too hard because every 1 hour has 60 minutes in it. So the hours units cancel. And now we have the linear speed in inches per minute. We can do some reducing. Notice that 15 goes into 60 4 times, so I'll cross out the 15, replace it with 1, and cross out 60 and replace it with 4. And we can do another reduction. 4 goes into 4 once and into 12 3 times, so I'll replace that with a 3 and that with a 1. So now the denominator is just 1 minute. And then 3 times 5,280 inches, let's see, that's just 15,840 inches per minute. Okay, so that's the linear speed in inches per minute. And we want to find the angular speed in radians per minute. So all I have to do to get the angular speed is divide the linear speed v by the radius, which is 12 inches. Okay, so the linear speed divided by 12 inches, we get 15,840 inches per minute. Since I'm dividing by 12 inches, I can just multiply 1 minute by 12 inches in the denominator. And this is going to convert to radians per minute, so the inches units cancel. And then, let's see, this is going to be, 12 goes into 15,840, 1,320 times. So 1,320 radians per minute is the angular speed. Okay, so one last thing. Find the revolutions per minute. Well, in 1 revolution, we have 2 pi radians. So if you just divide omega, the linear speed, divide that by 2 pi. So we get 1,320 divided by 2 pi. This is going to be per minute. So this is just going to come out to be 660 over pi revolutions per minute. Okay, another review problem. Given a circle with radius 10 inches, find the area of the sector if its central angle is pi over 5 radians. Okay, a sector of the circle so I won't draw the whole circle. This is just a part of the circle. The radius is 10 inches. The central angle is pi over 5 radians. And then there's an arc length. So first, let's find the area. So the area of the sector is just a fraction of the area of the entire circle. So the fraction is the size of this central angle, pi over 5 divided by 2 pi, multiplied by the area of the entire circle, pi r squared. And the radius is 10, so let's simplify this a little bit. We can, if we divide pi over 5 by 2 pi, that's equivalent to multiplying pi over 5 by 1 over 2 pi, multiplied by pi times 10 to the second. And then we'll just do the arithmetic. So these pi's cancel, so I'm going to get the area equals pi over 10 times 100. And pi over 10 times 100 simplifies to 10 pi. And then we should include the units for the area. Since the radius is given in inches, this will be square inches for the area. Also find the arc length. So in general, the arc length S is equal to the radius times the central angle. So in this case, the radius is 10 inches. And the central angle is pi over 5 radians. So the arc length is 2 pi inches. I have another problem that's pretty much like the one that we just did, but we'll bypass that for now so that we can look at a couple of other problems. Okay, this one says use the cofunction of the complementary angle to complete the equation. So I'll remind you, if you have cosine of pi over 2 minus theta, that's equal to the sine of theta. So in this case, cosine of pi over 6 well, if you think of pi over 6 as pi over 2 minus theta, then theta would be pi over 3. So cosine of pi over 6 is equal to the sine of pi over 3. We already knew that. Remember that cosine of pi over 6 is the square root of 3 over 2, and sine of pi over 3 is square root of 3 over 2. Okay, and the next one, in a right triangle, the length of the side opposite of a 30-degree angle is 7. Find the lengths of the two other sides. Here we have a right triangle. One of the angles is 30 degrees. So that means the other angle is 60. And the side opposite of 30 degrees is length 7. So let's find the hypotenuse H, and this side I'll call A. So we can use any of the trigonometric functions to help. We can write sine of 30 degrees is equal to the length of the opposite side divided by the hypotenuse, 7 divided by h. And then we can solve this for h. Sine of 30 is 1/2, so we get 1/2 equals 7 divided by h. And so h is equal to 14. To find the length of the other side, so we now know that the hypotenuse is 14, we can use cosine of 30 degrees is equal to the adjacent side, A, divided by the hypotenuse, 14. And so A is 14 times the cosine of 30. I'll go ahead and write that. But the cosine of 30 is the square root of 3 over 2. So A is 7 times the square root of 3. Okay, the next problem this one's a little more challenging than what we've done, but not too bad. We want to find the value of x, which is just the length of this part right here. So we can use right triangles. We have two right triangles to work with. The smaller right triangle, since this angle is 56 degrees, this angle has to be 34 degrees because they have to add up to 90. And then, well, in the bigger right triangle, this angle, this big angle up here, has to be 55 degrees. And just to help, let's refer to this length right here as y. So now we can use trigonometry to determine what the value of x is. So let's look at the big right triangle first. And this angle up here is 55 degrees. So the tangent of 55 degrees is the length of the opposite side divided by the adjacent side. So the opposite side is x plus y, and the adjacent side is 115. So we can write this as x plus y equals 115 times the tangent of 55 degrees. Okay, now let's look at the small right triangle. So in the small right triangle, this angle up here is 34 degrees. So we can write the tangent of 34 degrees is equal to the opposite side y divided by the adjacent side 115. So y divided by 115. And so y is equal to 115 times the tangent of 34 degrees. Okay, the goal is to solve for x. So now all we have to do is replace y in this equation with 115 times tangent of 34. So in other words, x plus 115 times the tangent of 34 degrees is equal to 115 times the tangent of 55 degrees. And then the last step, subtract 115 times the tangent of 34 from both sides. So the x value that we're looking for is 115 times the tangent of 55 degrees minus 115 times the tangent of 34 degrees. Okay, we're out of time for today. Tomorrow we'll start a new section. We'll cover two sections tomorrow, 7.4 and 8.1. That's all for today.